Right. Thanks, everyone, and welcome to our second paper session on light transport and storage. Our first speaker is Kenta Ito from AMD Japan, where he does rendering R&D and is interested in both offline and games applications. Kento, before AMD, got his MSc in mathematical finance from Tokyo Institute of Technology, and he's going to tell us how to get better, less noisy reflections using bounded VNDF, visible normal distribution function sampling for the Smith GGX BRDF.
Yeah, thank you for the introduction. So hello everyone, I'm Kenta Ito. So today I will talk about our work, bounded VND sampling for the Smith GGX BRDF. So this method is already introduced in last year's SIGGRAPH Asia as a short paper. But in this presentation, we will show more detailed discussions and new experiments related to energy compensated BRDF. So let's start. Before going into the details, let me introduce the background first. So in the computer graphics industry, such as video games, the Smith GGX microfaceted BRDF model is widely used to represent glossy materials. Microfaceted BRDF is composed of Fresnel function F, masking shadowing function G, and normal distribution function D. And in Smith GGX microfaceted BRDF, we use the Smith model for G and the GGX normal distribution function for D term. This model can represent reflective surfaces of various roughness settings. The right image shows the rendering result of the Smith GGX microfaceted BRDF. By using this BRDF, we can render low frequency reflections, also highly glossy reflections, by changing the roughness parameter of the BRDF. In the usual single scattering microfaceted BRDF, it is known that it has a darkening material appearance for high roughness due to the lack of multiple scattering term. The following image shows the rendering result of the single scattering Smith GGX BRDF. In high roughness settings, you can see some darkening of the rendering result. To solve this problem, lookup table-based energy compensated BRDF is often used in productions. There are mainly two methods. In Kura and Cotti's method, they added additional diffuse term to compensate for the energy loss in single scattering BRDF. In Tarkin's method, they scaled the microfaceted BRDF to compensate for the energy loss. Both methods fixes the darkening problem for high roughness as shown in the image. So when we want to render the surface by ray tracing, we need to sample outgoing directions from the BRDF at the shading point. Sampling according to a visible normal distribution function, VNDF, is widely used to sample those ray directions scattered from the Smith GGX microfaceted BRDF. Although VNDF sampling is especially efficient for highly glossy materials, it is not always efficient for rough surfaces. The sample direction can go under the object's surface, as shown in the right figure. And for reflection rendering, we need to discard such zero contribution samples. It makes the sampling efficiency worse and increases the noise in the rendered image. Also, this discarding increases the code path divergence and reduces the thread occupancy on the GPU. Thus, it can be inefficient for GPU-based real-time rendering. Also, we found that such samples can produce fireflies for lookup table-based energy compensated BRDF. This is significant on highly rough surfaces. In our work, we reduce such zero contribution samples and increase the sampling efficiency of VNDF sampling. Now, let's move on to our method. Before going into details, I will explain an overview of our method. First, our method is based on the state-of-the-art VNDF sampling method that uses a spherical cap domain. In our work, we introduce a tighter bound for this spherical cap-based sampling range. As shown in the image, the green line is the previous bound, and the red line is our new bound. By moving up the previous bound, we reduce zero contribution samples. Let me explain our advantages of our method. So, by generating samples from our bounded spherical cap, we can reduce the number of zero contribution samples for VNDF sampling. Also, it reduces fireflies for energy compensated BRDF. Finally, our method is very easy to implement. The right image shows the implementation of our method. The yellow text highlights the addition of the code in our method. It only adds 5 lines of code to the existing sampling routine and PDF routine. In the previous VNDF sampling method, visible microfacet normal is sampled by stretching the tangent space. First, we stretch the view vector to the stretched space, like this. The stretched space corresponds to the space where roughness x and roughness y are both 1.0. Then, we sample a microfacet normal using the spherical cap and stretch under the stretched view vector. At this time, the sampled microfacet normal is in the stretched space. Finally, we unstretch the sampled microfacet normal and get a reflection vector in the unstretched original space. In our work, we derived an analytic boundary which separates the contribution and zero contribution samples on the sampling space. In this figure, the yellow line is derived boundary. The orange area represents the region where samples will not be discarded. And the blue area represents the region where samples will be discarded. So, if we can sample from the upper yellow area, we can remove zero contribution samples. By taking minimum z value of the boundary, we derived an analytic lower bound to limit the sampling range of the spherical cap. Let's compare our new sampling range with the previous method. In this figure, the green line shows the bound of the previous method, and the red line is our new bound. The bound of the previous method is located around the bottom of the sphere. But our bound is closer to the boundary. Thus, we can reduce the zero contribution samples. For the anisotropic roughness, we introduce a bound by reusing the lower bound from the isotropic roughness. It is slightly looser than the isotropic bound. However, it is still analytical and easy to evaluate. Since we only changed the height of the spherical cap from the previous method, the sampling algorithm is simple and only requires slight change from the previous method. Our method is also applicable to energy compensated BRDF. So we found that the previous method can produce firefly noise for energy compensated BRDF. This happens because the PDF of the previous method doesn't match the shape of the energy compensated BRDF. In this figure, the blue line shows the shape of the energy compensated BRDF, and the green line shows the PDF of the previous method, and the red line is our PDF. As you can see in the figure, our method has higher density samples than the previous method. Therefore, our method reduces the firefly noise caused by multiple scattering approximations for rough surfaces. Now, let's move on to our results. We compare our method with the previous method in this test scene. This test scene has objects that have the Smith-Jejex microfacet BRDF with several roughness settings. We use path tracing using multiple importance sampling of VNDF sampling and next event estimation. To approximate multiple scattering on the microsurface, we use Tarkin's energy compensated BRDF. This is a close-up of the result. The first row shows the rendering result from the previous method. And the second row shows the rendering result from our method. In the close-up image, the black pixels correspond to zero contribution samples. By using our method, we can reduce such a zero contribution samples, and the RMSE becomes lower in our method. Please note that the rendering time is slightly increased in our method. This is because the increase of the depth of the rays path. Although our method increased the path depth, our method reduced the code path divergence, especially at shallow path depth in path tracing. Therefore, the increase in rendering time is insignificant compared to the improvement in rendering quality. This slide compares our method with the previous method in various roughness settings. Images in the top row shows the rendering result. The bottom row shows the RMSE number of the rendering result. In the rightmost image, the difference of RMSE between our method and the previous method is larger in high roughness settings. That shows our method performs well in the high roughness settings. This is because the difference between our bound and the previous bound is larger in such a high roughness case. In the middle image, the difference of RMSE between our method and the previous method is smaller in highly anisotropic settings. That shows the merit of using our method is smaller in such a high anisotropic case. This is because we introduced the conservative bound for the anisotropic case. It is one of the limitations of our work. Here, we show the rendering result of applying our method to the energy compensated BRDF. This is our test scene. We conduct the experiment on two different types of energy compensated BRDF, Kura and Conti's BRDF and Tarkin's BRDF. So this is a close-up of the result. The first row shows the rendering result from the previous method, and the second row shows the rendering result from our method. In the previous method, there are noticeable fireflies on both energy compensated BRDF. Please note that this experiment is using very large number of samples. Even with this large number of samples, the previous method can produce such a fireflies. In our method, those fireflies are significantly reduced and on both energy compensated BRDF. And the RMSE is also significantly improved. Now, let's move on to the limitations and conclusion. First, our method is specialized for reflections. It cannot be used for sampling refraction direction. Also, it cannot be used for random walk multiple scattering algorithm, since our method cannot sample reflection directions in the lower hemisphere. Second, our method increases the rendering time by increasing the ray's path depth. But our method improves the cost effectiveness of the sampling. Third, our method still can produce zero contribution samples. This is because we are using the conservative bound for the sampling. In future work, we would like to completely remove zero contribution samples by sampling only from the yellow area as shown in the right figure. Finally, I will give a conclusion. First, we derived a new sampling method specialized for reflections to reduce the number of zero contribution samples in VNDF sampling. Second, our method reduces the variance of the rendering result for highly rough and low anisotropy surface. Third, our method significantly reduces fireflies for energy compensated BRDF. Finally, our method is very easy to implement. It requires only 5 lines of code. So that's all for my presentation. Thank you all for attending.
All right. Do we have any questions? I can start with one while people are still thinking of them. So Anis Benyu from the Intel paper that was yeah, sorry. The authors of the Intel paper had a special version that they came up with after the fact for isotropic GGX. So in that case, you can do the VNDF sampling without constructing a tangent frame.
Yeah.
Do you know whether your method also works in that case? Especially since you showed that it works better in the isotropic case, which is a pretty important special case.
I'm actually not sure, but basically our method is based on deriving the mapping between the original space, unstretched space, and after the stretched space. So if we can like derive similar mappings in their method, I think we can do the same thing. But the problem is that such a mapping can be very complex depending on their method. So if we can derive such a mapping, if it's not in the simple form, we cannot derive the simple sampling algorithm. So that could be a problem. Answering your question.
Other questions? I could just maybe follow up on that. About the case of refraction, is it a similar thing that the mappings are just sort of sufficiently complex that you don't have an easy way of deriving a bound for them? Or
Yes.
Is there some more fundamental limitation?
Yes, because the refraction sometimes it can include the total internal reflection. So the mapping function will be very complex form. So it's not easy to derive the simple sampling algorithm for such a case. Yeah.
Last call. All right, let's thank Kenta again.
Yeah, thank you. So I just. Thanks.
All right, so our next speaker truly needs no introduction, which is good because he didn't provide me with much. But seriously, if you don't know who he is, he has a Wikipedia page, so you should look him up. He just wanted me to let you know that he is now at Activision. So I'll hand it over to Peter Shirley, who will tell us about ZH3 quadratic zonal harmonics.
Gave them a PDF, so that was my fault. I was going to say what my first I3D was to give you some fodder for the introduction, and I looked at the list and I can't remember. So that tells you more than anything else. So this is why we're still looking at baking. So I can fight people in the reception if they want to. I am actually a huge fan of baking now. The last year has convinced me baking is here to stay. So we can have some proposition bets tonight over drinks, but I won't go into that now, but just take that as a given for this talk. Baking is not dying. I think it's actually going to increase in its use cases. And this is why we're so concerned about storage at Activision. These models that we have are just ginormous, and they do affect gameplay. Like, these are the models I actually prefer to play in when I play the game. So storage is one of the biggest problems in games right now. Just things are huge, so everything is about compression. The best way to compress things is to make the data not very big in the first place before you have to compress it. And there have been a lot of things looked into for how do we store these probes. That's usually what these spheres that say what light's coming from what direction. How do we store these things so that they're compact and expressive? And some of the early solutions were tables, and then there were spherical harmonics. And I'll tell you, I've always hated spherical harmonics. My undergrad advisor told me to use them in the 80s, and I was like, they ring, they have negative. Things that have negative just offended me. And so I've been fighting these my whole career. People have tried to do various alternatives, including things I have done, but punchline, spherical harmonics are the right answer. This is an empirical result. This happens in computer science all the time. It's not clear why some method seems to work so well over time. Sometimes it takes a long time, things come and go, so like we know now, neural nets are the right method, whether you like it or not. That's just true. I feel that way about spherical harmonics now. So just a little background. Many of us saw Fourier analysis in some undergraduate course, and for this kind of periodic, discrete Fourier analysis, you keep adding cosines together, good things happen. The catch is it's cyclic. And so you have this repeating pattern, you have boundaries, pain in the neck. In computer graphics, we have spheres, not just lines. Spheres are pain in the neck. They're surprisingly subtle. They're weird. They cause you a lot of pain. But the good news is, periodic's not a problem. The sphere is also periodic because it just doesn't go forever. So this repeating thing, it's the one good thing about spherical harmonics, just intuitively, is you don't have to worry that much about it. A problem with spherical harmonics is they have these cosine-like basis functions, kind of a sphere analogy of Fourier analysis, and they're really hard to graph. So different people have different methods. I went on Wikipedia just to see what people used. The favorite one is the one on the right, which it turns out, I found out on Twitter, is by one of our friends. He has a shader toy that's what ended up on Wikipedia. Those are the pictures I will use. So all it is in a direction, give me a number. That's the function you have. And there are various ways to map that out. The method on the right is the radius of this projected shape is the value of the spherical harmonics. So let's just say a little about those, because I know right now, if you're like me, you're like, oh crap, another spherical harmonics talk. I don't want to see these equations. Let's just talk a little about why did they win? What's so powerful about spherical harmonics that they somehow seem to have won despite all of their annoying things for a graphics person, like negative energy? So first, this is remarkable to me. It's also true of Fourier analysis in 1D. They're steerable, or on the sphere, you might call that closed under rotation. So it's not at all obvious, but that middle row of the linear terms, if you sum those together any way you want, you end up with a dumbbell shape. Like those, they rotate. So it's very obvious that it doesn't matter what coordinate system you use, they can express exactly the same functions. It's a very good feature computationally. They're orthogonal, and their linearity and orthogonality end up just paying bonuses all over the place empirically, which is why they seem to win empirically. Oops. I'm skipping ahead by hitting the wrong button, pardon me. So if you take any of those functions and multiply them together and integrate at 0, not totally obvious if you look at some of them, like that one in the middle on the bottom with some of the others. But if you think about the negative and positive regions and the symmetries, actually does make some sense. I really have to get rid of my tremor, apparently. They're easily convolved. This is very important because you take this light field, you multiply it by a BRDF, that's convolution, and you integrate. So let's talk about spherical harmonic lighting in games. Like I said, compression is key. Small shaders is key. You just don't want much stuff. And Ravi showed back in the day that the quadratic basis functions, so the complete set of ones I showed earlier, the linear and quadratic terms, really work great for diffuse surfaces. You pretty much get the right answer. So if you look in the middle there, that bunny illuminated with an environment map and coded as a spherical harmonic versus the reference solution where you just path trace that sucker look very similar. but we would really like to store just the linear basis because it's half the size. And also faster. As you note, though, it kind of sucks at how it illuminates that shape. So what this paper is about, spoiler, is we want the quality of the middle with the storage of the top. And it turns out that is totally possible. It's been shipped. It works. There's very few downsides to that empirically. So this is just a super well-loved technique now within our company. A little bit of terminology. The middle terms, this is all of the spherical harmonic bases. And my clock went into power save mode, pardon me. Oh, and it died. Hey, can you give me a time when we're 5 minutes out or something? Thanks. So that middle set of functions, notice, is symmetric about the z-axis. Those are called zonal terms. So when you hear some spherical harmonic zealot talking about the zonal terms, that's what they mean. It's just that middle row. And it really is an odd man out. They look very different than the other terms in that. And what we're going to do is say, hey, we're going to take the really cheap version, which doesn't have the quadratic terms. The quadratic terms are that bottom row. We're going to just add that one weird zonal term, and then life will be good. And that is the summary of the paper right there. So it gives a really good middle ground if you just have that one little extra term. In practice, ZH3 is just the one extra term. The SH3 is the all of those bottom row terms. So largely they look much the same. And that in practice is why we use it. There is one little bit. It's no longer orthogonal when you only have that one extra term. Or I should say, it's no longer closed under rotation. And you have to do this for red, green, and blue. Things come out a little different, and you get a little bit of color ringing, basically. And so if you just do an optimization to share the axes on that one extra term, so note, if we only have that one extra term, suddenly things aren't closed under rotation. We need to pick an axis. This kind of seems to undermine one of the best things about spherical harmonics. And don't we have to store 3 extra numbers? If we store an axis, it seems like loss. The linear terms have an implicit axis in them. It's different for RG and B. We can make them share it and then not have to store anything. And so this is a little nuance of the paper. If you implement this, this is very important. But I think this thing that's pushed this over the edge, we'll use this a lot more because it just lacks color artifacts, which are always a danger. We can solve for that axis. Key thing is it's a nonlinear optimization. Whenever you do that, something bad is going to happen to you elsewhere down the line. It's like you've committed a sin. And this will not quite interpolate as well as if you haven't done a nonlinear optimization. So that's just something to keep an eye on. In practice, this seems to work well, though. Here's my favorite part of this work, and it's remarkable to me. Well, there's a lot of order to the way light works in the world. Can't we just make that axis up, that last extra term we used? Just make it up out of whole cloth? Answer, yes. It's not perfect, but it's a whole lot better than just not having that coefficient to just guess it. And I'll leave the details to the paper for you. So here's an example of that hallucination. The reference solution, path traced, is on the right. And that hallucinated version is surprisingly close and is better than the previous work that also did a hallucination. Now, this is one of many examples of there's a lot of priors in computer graphics that we implicitly or explicitly figure out. This we just did by data fitting. So there is some order in the way environment maps seem to work. We will exploit that order without necessarily understanding it. Here's the really important part. It's just not much code to hallucinate that. So totally practical in games. It's shipped. So the beauty of this is the optimization is a pre-process, so now it just generates an empirical formula. And then there's some results here showing that the mean square error is lower. I got to note that when I see mean square error in a paper, I always ignore it. I only look at like pictures of bunnies and stuff because the mean square error in the end doesn't matter that much. But reviewers like it, so we're going to include it. So now some results. This I do look at. So here is linear spherical harmonics, which is just those 3 terms in addition to the DC component. And there's some weird color stuff going on. For all you know, this is right. Quadratic, which is what we'd really like, all sorts of color artifacts went away. Oh man, hitting the wrong button again. All sorts of color artifacts went away with quadratic. So we want quadratic in the game. Linear doesn't suffice. Here's linear again, weird artifacts. Now, watch carefully. Quadratic, where we've added an extra term. Here's where we make it up out of whole cloth. Just make it up. Remarkably close, and much closer than much closer than linear. Okay, one more time. I'm not touching it. It's hallucinating to touch. So here's linear. Quadratic, we've added that one extra term. Hallucinate the ZH3. Oh, I lied here. That's full quadratic. So full quadratic's much better than linear. The same memory as linear, but hallucinating one extra term, and we get something shockingly close. I'm actually amazed at how well that works. So here's a bonus. And what is my time looking like since my clock went out? So this is a really key thing about encoding spherical harmonics. This is something that has been developed long before I got into the games industry by extreme experiment of trying to bleed every single bit out. So if you encode, and I'm going to go through the stored. Oh, I figured out what's going on. It's a touch screen. Okay. So you can always spot a Mac user when they end up with one of those. So if you have stored ZH3, let's say what that is again. Linear spherical harmonics is just those top 4 terms, a DC component and 3 linear terms, 1 for each axis. Stored ZH3 is those same terms plus 1 extra float for red, green, and blue. And that will give you 16 bytes for every one of these probes. So if we look at it, why 16 bytes? We need a DC component. That DC component is high dynamic range. So somehow we have to have 3 floating point RGBs that are high dynamic range, and we need to stuff them somehow. Common method is 11 bits for red, 11 for blue, or 11 for green, and 10 for blue, because blue's always the short person out. Those white lines are just 4-byte chunks, just for your visualization. And then the other terms, we can just stack in 3 for the first term, 3 for the second, 3 for the third, and then the ZH3 term gets the final 3 bytes. So it just packs up really well. Now, a terminology thing. Why is there a stupid 3 there when it has quadratic terms? Because last I checked, quadratic terms have a 2. This is just one of the original sins of the spherical harmonics literature and the spline literature was order and degree get very confused. So just accept that you're not misunderstanding anything. Someone old enough to be your grandparent made some very bad decisions about terminology, and we're stuck with them. Key is it's quadratic, therefore it's a 3. Mother. Okay. So you can see how we're using it. It's shipped in a bunch of games. There are a bunch of probes in different parts of the Lightning pipeline. Most of the variations of this that you have seen have shipped in games. The ZH3 one we're very fond of right now, and I kind of think it's reached an asymptote where that's the one that is just going to be the most powerful because it fits so well in computer memory, and it seems to work so well in practice. And if you want to go see the code, here's a shader toy. So this is my favorite use of QR codes out there. Is in a talk. You can just get it. So grab that QR code and you will get a shader toy implementation. Oh, let's wait because I went fast. Yeah, exactly. These things that come and go, like, neural nets went away and then it came back. QR codes are one of those things. It's interesting. They almost died and now they are everywhere. And why that's true is not exactly clear to me because they were always useful. That's usually a good default hypothesis for anything, actually, so I'll buy it. Thank you. Sadly, there's a person that's deceased that was involved in the early work on this, so we're honoring him here. And then there's a whole bunch of references that should all be available. I think all of these are available on the web now. So thank you.
Questions? Yeah.
Amazing work. And I was also always annoyed by spherical harmonics and their annoying properties, but also have used them in many, many titles and very often using this geomerics trick that you cited there. And so I've been also wondering about this work because you focus here, I imagine, specifically on light probes because you're taking into account its whole sphere radiance and this periodicity, etc. It all works out. Do you have any intuitions, etc.? How were there any insights or lessons from this particular project that would also translate to something that works on hemisphere? And I know there were work like H-bases, etc., where people were adapting spherical harmonics specifically to hemispheres. But do you have any insights whether your particular work, are there any insights that could apply to surfaces and hemispheres?
I do not, but, big but, there's a tech report on that exact subject being put up by the first author of this paper. It's very nice, should be up hopefully within a week or two. And the hemisphere is a really nasty thing. So a sphere is nasty. It's much worse than planes, but a hemisphere is like a nightmare. And then often we have two hemispheres when you have incident direction, exiting direction. And so stay tuned. Watch our webpage. That should be appearing. And if I had insights myself, I would give them to you. But anything I know is somewhat understanding that paper. It's much more complicated. I was surprised to see, though, once you really start thinking about it.
Thank you.
Hi, thank you. Very interesting, really cool work. I was wondering, you did this for 3 bands. Does it extend to 4 bands? Can you do the same trick, or?
For like an alpha or something like that, or?
I was thinking if you had like 4 bands of spherical harmonics, can you do the same thing?
Oh, the spherical harmonics, not the RGB. Okay,
yeah, coefficients
okay.
is what I'm talking about.
Yeah, so probably, but I don't know. One of the works that I said was a sort of an alternative to spherical harmonics that I listed there was by Michal Iwanicki, and he used 2 non-spherical harmonics terms to try and get a lot of detail in the sphere, and he sacrificed the orthogonality. And in the end, it did work, but some of the bytes that you got from throwing away the orthogonality was too high a cost to pay in practice for our application. But for a different thing, like the hot thing for spherical harmonic now is NERFs, which some of you may have heard of, right? Because you need to represent something. And it might be very good for that, because there you might want more detail, for example, than we need, because we're going to convolve it with a cosine lobe, and the NERF people are not, right? So higher order things. And if we want to do glossy things, we also would want more. And that might pay off. But I kind of feel like empirically, man, you want orthogonality when you can get it.
One question. I'm excusing myself to ask a systems question here, if that's okay. So, to my eyes, like the approximation still had some color shift, and you said that you already shipped it. in production, do you need to do any sort of like post on that to make it work?
As far as I can tell, no. But you never know. So one thing is, any new map some artists do might bring up some weird bug you have that you don't know about, or not even bug, characteristic, negative characteristic of your algorithm. But as far as I know, no.
Thanks.
I'm going to ask something. Since you were talking about squeezing every bit out of things, is there any value you think in using like shared exponent formats or something, sharing something between the RGB channels?
So this was my exact question on why do we use that 11, 11, 10 encoding? Because in practice, it's lost out to the shared exponent encodings before my time. Like this I guess battle has been won over years. And in practice, when you have a shared exponent, you don't have the implicit 1 on the mantissa. And those 3 implicit 1s pay off more than the shared exponent does in practice, and that's an entirely empirical result.
Interesting, thanks.
I have a quick question. So I'm curious, like, does this method work for things that have internal reflection, like raindrops or like ice?
I would think no, because that has a lot more detail. Now, if the zonal hallucination stuff work for higher dimensions, more rows of those spherical harmonics, maybe. But certainly we haven't tried anything like that.
Okay.
I'm gonna ask one more. So since you started off by saying how you hate spherical harmonics, it seems like what you have is
I hate it. I'm reformed. I'm
You're
reformed.
okay. I'm sorry. I didn't.
I will accept victory
I don't mean
when
to
something
besmirch
wins.
your view, but if you had it, if someone were to have it in for spherical harmonics, it seems like what you have is in some sense a strict generalization of that, in the sense that really it seems like what you're doing is you're using the L equals 1 spherical harmonic to choose an axis, and then you're fitting a zonal function, really. Like you're fitting a quadratic in your case, but you might think, well, it doesn't have to be quadratic. For example, the geomerics one was not quadratic. Representations like spherical Gaussians are very similar. They have an axis, and then they don't try to do a linear fit. They just fit an exponential, and you could imagine, given that you're sort of empirically matching to data, that you could try to fit a more general class of functions. So have you thought about this generalization?
A sum of strictly non-negative basis functions is much more appealing to me that you non-linearly fit, because I hate negative light, pisses me off. But that has not worked out. I mean, people have tried it. Again, this is just an empirical thing. And Ivanicki in particular, who I talked about, he's really tried to push that a few times, and it just hasn't worked out in the trade-off space. So the negative light and the ringing really in practice just doesn't seem to be a real problem. It seems to be a math nerd problem. So it does bug me. But so no, nonlinear optimization considered evil, I guess, is what ends up being the practical result. But I would love to be proven wrong. Like, as much as I've just surrendered to spherical harmonics, if one of you can do something better, I'd love to read your draft.
All right, I guess the gauntlet has been thrown down. So let's thank Peter again.
Thank you.
Okay, so the last speaker for our session is Ana Granizo Hidalgo. Ana has a master's in computer science. She is a final year PhD student at Université Grenoble-Alpes, if I said that right. And she is interested in realistic image synthesis, and she is going to tell us about interactive rendering of caustics using dimensional reduction for manifold next event estimation. Take it away, Ana.
Thank you. Good afternoon, everybody. Thanks for the introduction. And as the title said, I'm going to talk about rendering caustics interactively. So let's start. So well, I think we all have seen caustics. There's the bright things that we can see under the water, and they are moving and dancing around, that they are beautiful. And actually they are caused because the light is traversing the water, which is a specular surface. And because the water is curved, what happens is that the light is going to focus in some places more than in other ones. And that's what's causing these caustics. So what we are interested in is to render these caustics, but doing it interactively. So for a start, a little introduction of what's happening actually behind this. So in refraction, what we have is we are going to follow up the path from the eye or the camera to the light. So we have the eye, we have one refraction, then we hit the ground, and then for connecting to the light, we're going to have another refraction, that's this point M, and we get to the light. For this to happen, this has to fulfill physical laws, especially the Snell law, that is going to tell us that the angle in which the ray that's is changing from the one medium, that in this case it's water, to another medium that it's air, this ray is going to change its direction, and this change in direction, this angle, it's going to depend on the index of refraction of each of the materials and also the normal at this point. So this is what's happening in real life, the physics of law, how this is happening. I also wanted to present how a small representation of what we have, bodies of water that we can see in video games and movies, because obviously if we want to present something that looks realistic, what we need is to try to mimic the physics laws. So for instance, here we have a scene that I'm not sure if you can really see, but we have some shadows in the water. In this case, we cannot find caustics in this sense, but I put it to represent the effects that we could want to add in our scenes. For instance, in this one, we are seeing that it's a lot of reflection in the water. Also, we don't see caustics, but we have reflection. Or in this one, that we can see the small waves that they make when the water is falling into some more water, and we have these waves that are forming because of the physics. And in all of these scenes, we don't see caustics. And I also found two options where we do have some caustics that help us to make more real the scene. In both of these cases, these caustics are created as textures that are mapped into the images. And that's the thing, that for generating caustics, it's really expensive to compute. So that's why in the other things that I showed, there are not caustics in there, because it's really too complicated to do it in real time. So as I said, in these other two options, we do have them, but they are a texture map. So they are not computed in real time. And I'm going to explain why this is difficult. So normally we have path tracing that we all know and love. To compute, we follow the ray from the light, or from the camera to the light, sorry. And we can improve this with the next 7 estimation, which works really good. We connect each point or every intersection with the light, and it's going to help us to make image really good. But what happens if we introduce a plane of or body of water in between of this? And the thing is that actually this image wouldn't be accurate anymore, because I mentioned we have some refractions that are happening when we cross from air to water and from water to air. So in this case, if we want to connect the point with the light as this, we cannot just send a ray directly from this point to the light and hit the light. We are not going to hit the light. Actually, this is going to be refracted and it's going to go somewhere else. So that's why this is difficult to find this path of light. We could try to sample randomly all over the place and try to get to the light, but actually this is not going to work. That's why Hanika and colleagues introduced manifold next event estimation. And what they do is to, using the same idea of next event estimation, connect the last point to the light. So they start with a starting fixed point that's connecting the point with the light and the intersection with the object. And then using an objective function that's based on the half vector of the angles, try to walk like a search in the object 3D to try to find this point that's actually going to be a path that connects with the light. This approach works well, but especially with not complicated objects. That's why Selnard and colleagues introduced specular manifold sampling. And the thing is that we can have more than one path that connects that point with the light. So with manifold net 7 estimation, as we do have only one starting point, we have just one solution. So specular manifold sampling, they introduce the idea of having several random starting points on the surface of the object, so we can find more of the solutions. And they also introduce a new objective function that it's going to be the difference between the angles of the refracted vector and a line connecting the last point with the light. So when these two are equal, so the difference between the angles is 0, so we have a solution. And both of these methods, what they are doing is they are searching for solutions of an objective function, different objective functions, but that's basically the idea. And both of them use the Newton-Raphson method to do this. The thing is that this search that they are doing, it's done in 3D space of the object. So our approach is to reduce the dimensionality of this search. And instead of having a 3D search on all of the object surface, we are going to have a 1D search on a curve that I'm going to explain a lot more better. And with this, we don't have to search the whole object, and we reduce a lot the complexity of the problem. So to do that, we introduce a coplanarity constraint. We have this point P, we have this point L, and what we want to find is this point M. We also, having these 3 points, we have the vectors, the incident ray from the point P to M. We have the refracted vector from M to L, and we have the normal at the point M. And we have 3 vectors that must be coplanar for the physics. They are coplanar, and to know if 3 vectors are coplanar, we can use the scalar tripler product. And when we have the scalar tripler product, so we have a valid path. So to do that, we are using everything in a mesh of triangles. So, okay, sorry. So we have the point M. No, it's not that one. Okay. We have our point M. It's going to be on the surface. So it's going to be in one triangle. For the moment, we don't care about which triangle it is. We just know that it's going to be in a triangle. And the better way to describe this point is in barycentric coordinates, because we know all of the vertices and the normals at each triangle. The position of the vertices and the normal at each vertex. So we represent this point M in barycentric coordinates. And we can also express any point connected to M in the same way. So we express PM and LM as a matrix vector product. And also, as we have the normals, I almost forgot to mention, we need to have interpolated normals. So we also can express the normal at point M in barycentric coordinates. With this, we have the 3 vectors that I mentioned before. So we can solve this scalar triple product. And if we solve this at the end, after a lot of computations, we are going to end up with a quadratic equation of a conic, like really simple, where alpha and beta are actually the barycentric coordinates. If we plot this equation for all of the values of alpha and beta, we're going to end up with a curve like the one in the top. That's a parabola, and it's in 3D, but we actually don't care about all of the values of alpha and beta. We are just interested in what's happened inside the triangle. So we only care about what's between 0 and 1, and also when this conic intersects the triangle. So we only care about this part here. And as you see, it's going to form a curve that is mapped into the triangle. So we can do this for each one of the triangles in the mesh. So here we have a water surface made of multiple triangles, and for one point inside of a pool and one point of light source, we compute the coplanarity constraint for each one of the triangles, and we are going to end up with something like this. That, and as I mentioned, we have interpolated normals, and that's what makes that this curve is continuous, because from one triangle to the next triangle, we are going to have the connection between. The curve is like this. So we have this curve. We know that our solution or path with the light is going to be inside this solution. So that's where we have reduced the dimensionality. Now we need to search only in this curve. So to do that, we need to have a starting point in the curve. And for that, we are going to use the same approach as Hanika and colleagues. And we are going to connect point P with the light and having the intersection with the surface as our starting point. And this point, we are sure that is on the curve because these 2 points are collinear. So now we have our starting point. We know that we are in the curve. And then we are going to walk in the curve. So we start with our starting point. And at each triangle, what we do is to compute the intersections between the curve and the edges of the triangle. So we compute this, and at each intersection, we are going to compute our objective function that I will explain later. But this function, what it's going to do is to guide us in order to know which direction to go and to know if we already have a triangle that has a solution and we stop walking. So we compute this, and we do that at each iteration, at each triangle, we compute the same, the intersection between with the edges and the objective function, until we get to a point that we reach a triangle that says that, okay, this triangle has a solution. We stop walking. And okay, so how do we know that this triangle has a solution? So our objective function actually give us sign. So if it's from one side of the solution, it's going to be positive. If it's at the other side of the solution, it's going to be negative. So it's really easy to know at each intersection, we compute the values of the objective function. If we have a change of signs between both of them, we know that this triangle has a solution. If they are the same, so we continue walking. So once when we are in the triangle with a solution, the way that we are going to find our specular point is we are going to use dichotomy to find the valid solution. So at each step, we subdivide the triangle and we compute the new intersection. And then we keep the triangle that has the change of signs. And we continue to do that until at one point we are going to reach that the intersection is going to actually be our valid path. The objective function that we are using is similar to the one of Salner and colleagues. We are using the difference between the angles of the refracted vector and the vector connecting the point M to the light. So once we have this point, we reach a solution, and we only need to compute the contribution of this point, and we have our rendering. So here I have some results. This is an implemented on Vulkan using the ray tracing extension on GPU. This scene it's performed at 20 milliseconds per frame, and it's a water mesh of 51K triangles, and as you can see, it's really interactive. We also wanted to do a comparison with the state of the art. So here's a comparison with specular manifold sampling. This method, it's not on GPU, it's on CPU. It's done at Mitsuba. So what here, it's actually not really animated. It's a compilation of several images. And each image, it takes 5K milliseconds per frame. So you can see the results are similar. And to have like a more equal comparison, we also compute our method in CPU on Mitsuba using exactly the same as specular manifold sampling, just changing the function that searches for the solutions. So in CPU, our method's a little slower. It's at 900 milliseconds per frame, but still it's a lot better than 5K milliseconds per frame, and we have basically the same solutions. We wanted also to compute how much it costs our method. So we did a computation of the same scene. We just changed the number of triangles that we have in the water. So this is how much time it costs to compute. It's an animated scene with reflection, refraction. And as we see, obviously it increments as we have more triangles because the complexity of the scene is more big. But to know how much actually our algorithm costs, we compute how much it takes without our algorithm, so without refraction and the caustics. And we can see here in orange that still it's like kind of similar. It's not that much the extra cost. So here we have the difference between both of them to actually see how much it costs. So it's interesting that at the beginning with less triangles, it does increase a little more quickly. So our algorithm costs a little more. But then it doesn't matter how much more triangles we have in the scene, our algorithm, it doesn't increase that much. So as long as we can have a lot of triangles and still our algorithm is not going to be a lot more slow. So we have some limitations, and we have only one starting point. And as I mentioned before, there are some cases with more complicated scenes that we can have more than one path. In our case, we're only finding one path, which makes that our method is also biased. Also, we could extend our method for reflection. Actually, the coplanarity constraint and searching the curve, all of that, it's going to work in reflection. It does work. But the problem is that we do need to have a starting point that is on the curve. And with reflection, this is harder to find. So this is another limitation. And finally, our method can get a lot more expensive if we use area light sources or glossy surfaces. In this case, we are using point light sources, and the water plane is perfectly specular. And to conclude, well, here we have an algorithm that finds the light of the path of the light through a refracted specular interfaces, like the water. We have reduced the dimensionality of the problem, introducing the coplanarity constraint, lowering from a 3D search to a 1D search. And at the end, we end up with an algorithm that is fast enough to be able to compute the caustics on real time on the GPU. Thank you.
Questions? Oh, yeah.
Yeah, so thanks for the nice presentation. My question is about the single starting point. So I want to know if the method can return multiple starting point by introducing some stochastic algorithm in your method, like starting from some random algorithm and then walk through some random directions in your method. So my question is like this.
So we could have another starting point. Actually, we did try with other things starting randomly, and we use gradient descent to get into the curve, and that actually works. But depending on where could be the starting point, if it's too fast, it will take longer. So the algorithm couldn't be in real time, but actually it does work. We have done it in CPU.
I see. Thank you. Also, the second question is okay. So in the walking through the triangles, you split the triangle by half, right?
Mm-hmm.
I want to know, how do you split the triangle? I think depending on the splitting axis, the search can take very long time. So I want to know about that.
That's not for walking, but when we are already in a triangle that has a
in
solution.
the triangle, yeah.
Yes, actually, because we have the curve intersects two of the edges of the triangles, so we split the last edges in half, and we just do that. Some cases could take, depending on where the solution is, could take some time.
I see. Yeah, thank you.
Hi. First off, this is incredibly cool. I can't believe I'm seeing this in 20 milliseconds.
Thank you.
I was curious you mentioned that you're like walking along the triangles like to find the neighbors and whatnot. Do you use any like fancy data structure for it, or like how do you go from I'm on this triangle to here's the one next to it along the curve?
Yeah, actually, we pre-compute a buffer of all of the neighbors of the triangle. So for each scene, we have to pre-compute that. Depending on the scene of the number of triangles, could take some time. But we do that one time, and then we just have it. So I'm in that triangle, and I do know which are my 3 neighbors. That's why it's easy to go to the other triangles.
Thanks.
More questions? All right, let's thank all our speakers.